In general, ceramic is an inorganic, non-metallic material consisting of two or more metallic and non-metallic elements. Unlike metals and polymers, which comprise mainly metallic and covalent bonding, ceramics are made up of ionic and covalent bonding. Ceramics can be amorphous or crystalline structures depending on the atomic arrangements. Ceramics can be classified based on composition as oxides, non-oxides, and composites. Both oxide and non-oxide ceramics are chemically inert. However, oxide ceramics such as alumina and zirconia are oxidation-resistant, electrically insulating, and generally have low thermal conductivity. In contrast, non-oxide ceramics possess low oxidation resistance, are electrically conducting, and have high thermal conductivity. There are different non-oxide ceramics, such as carbides, borides, nitrides, and silicates. On the other hand, composite ceramics are made of different combinations of oxides and non-oxides and, thus, in general, have variable thermal and electrical conductivity. Another way of classification is based on forms, such as powders, coatings, and bulk shapes. Powders are dry, solid particles of various sizes that are not cemented together. Coatings refer to films or deposits on substrates, whereas bulk shapes refer to the densified form of ceramics. In addition to general forms and composition, ceramics can be classified according to their reactivity as inert ceramics, degradable or resorbable ceramics, and surface reactive ceramics. Inert ceramics are chemically stable, they do not corrode, wear, or react to the host environment, and little or no chemical change occurs during the long-term exposure of inert ceramics to the physiological or host environment. Examples of inert ceramics include glass, zirconia, alumina, and diverse forms of carbon. Degradable and surface reactive ceramics react to the host or physiological environment, resulting in surface or bulk chemical changes. Bioactive glass is an excellent example of surface reactive ceramics, and hydroxyapatite and tricalcium phosphate are examples of resorbable ceramics. One term commonly used is bioceramic. Bioceramics are a class of inorganic solids with ionic and covalent bonding, typically processed at high temperatures. The term bioceramics essentially refer to only those ceramics that are in dare for use for biological applications. Nowadays, a wide range of ceramics and glass materials are used in structural functions as joints or tissue replacements, as well as coatings, to improve the biocompatibility of metal implants. Ceramics have also been used as carriers for growth factors, antibiotics, and drugs. Some important characteristics of bioceramics include their mechanical integrity and physical and chemical compatibility in the host or biological environments. In addition, implantable bioceramics should have the following properties: non-toxic, non-carcinogenic, do not induce allergic reactions, do not induce inflammatory response, induce tissue regeneration if needed, and influence tissue integration if needed. One of the advantages of ceramics is the large compressive strength and better wear resistance due to high hardness and elastic stiffness. While the compressive strength is almost identical to tensile strength in magnitude for metals, the compressive strength of ceramics can be 8 times larger than the tensile strength. In many biomedical applications, such advantageous properties are utilized. Nevertheless, the brittleness of ceramics remains a crucial issue regarding their reliability in clinical applications. The biocompatibility of ceramics largely depends on the microstructure, particularly the grain size. Although the biocompatibility of conventional ceramic materials such as alumina, zirconia, titania, hydroxyapatite, and calcium silicate is well established, their clinical applications are constrained. Some bioceramics commonly used today in medicine and dentistry are silicate glass, alumina, zirconia, carbon, calcium phosphates, hydroxyapatite, tricalcium phosphate, calcium sulfate, and bioactive glass. Silicate glass is composed primarily of silica, also known as silicon dioxide, commonly occurs as sandstone, silica sand, or quartzite and is formed by strong, directional covalent bonds. Interconnecting multiple CO4 tetrahedral units form silica into a three-dimensional network structure. Two CO4 tetrahedral can be connected by an oxygen atom known as the bridging oxygen. The flexibility of the oxygen bridge between the two silicon atoms permits silicon dioxide to exist as a polymorphic material, exhibiting both amorphous and crystalline structures. Its properties permit it to be used for abrasives, refractory materials, fillers, and optical components, as well as in high-temperature and corrosive environments. The three crystalline forms of silicon dioxide are quartz, cristobalite, and tridymite, with each of the crystalline forms capable of exhibiting allotropic transformation. The stability of its crystalline forms is highly dependent on the energy of the crystal structure. At any given temperature and pressure, the most stable crystalline form is the structure with the lowest energy. Changes in pressure and temperature can result in two types of transformations, namely displacive and reconstructive. As you can see in the figure, at high temperatures, silicon dioxide fuses together. Rapid cooling of this fused dioxide locks the atoms in a rigid structure and does not give them enough time for the formation of an ordered or crystalline structure. Depending on the application and the properties needed, the characteristics of silicate glass can be varied by changing the composition and cooling rate. Alumina is aluminum oxide commonly used in orthopedics and dentistry. High-purity alumina is a fine white material that is similar in appearance to common salt. Besides being called alumina, it is also called corundum, sapphire, ruby, or aloxite. Alumina is insoluble in water and organic liquids, but slightly soluble in strong acids and alkalis. It is used in abrasive, ceramics, and refractory industries. There are many grades of alumina, with high alumina grades having at least 99% purity. The amount of impurities and alloying agents account for the differences between the different alumina grades. The American Society for Testing and Materials specifies that alumina implants should contain greater than 99.5% of alumina and less than 0.1% combined silicon dioxide and alkali oxides. The different forms of alumina are dense, non-porous, and nearly inert. These ceramics are tough and scratch resistance, second only to diamonds. The mechanical properties such as strength, fatigue resistance, and fracture toughness of polycrystalline are a function of grain size, porosity, and purity. In this case, the finer the grain size or the higher the specific surface area of alumina, the higher its opacity will be. Similarly, the finer the grain size or higher the specific surface area, the higher its strength will be. Zirconia, also known as zirconium oxide, is a white crystalline oxide of zirconium. This ceramic occurs in three polymorphic forms. At room temperature, it exists as a monoclinic crystal structure. Zirconia exists in a tetragonal phase at temperatures between 1170 and 2370 degrees Celsius. A tetragonal monoclinic transformation occurred when zirconia ceramics cooled below 1170 degrees Celsius. A cubic phase is formed at temperatures above 2670 degrees Celsius. These transformations induce volume expansion, significant stresses, and cracks upon cooling from high temperatures. As a result of these volumetric expansions due to temperature-sensitive phase transformations, zirconium oxide ceramics are not suitable for use as a biomaterial. One of the solutions for this volume expansion during the phase transformation is the addition of different stabilizing oxides, such as yttrium oxide and magnesium oxide, which stabilize the tetragonal and cubic phases by producing multiphase materials known as partially stabilized zirconia. The stabilized state of zirconia is useful as a biomaterial. Carbon is a common element that exists in many allotropic forms, such as crystalline diamond, graphite, non-crystalline carbon, or quasicrystalline pyrolytic carbon. It can be fabricated as powders, fibers, sheets, blocks, and thin films. The properties that are desirable for this biomaterial are excellent electrical and thermal conductivity, low density, sufficient corrosion resistance, low elasticity, and low thermal expansion. One of the common carbon forms used as a biomaterial is pyrolytic carbon, which is widely used for implant fabrication and surface coatings. In addition, it is often used as an artificial heart valve material due to its excellent strength, wear resistance and durability, and thromboresistance. Pyrolytic carbon is also used to fabricate small joint implants such as fingers and spinal inserts. The pyrolytic carbon used in implants exists in two forms: low-temperature isotropic carbon, LTI, and ultra-low-temperature isotropic carbon, ULTI. LTI carbon exhibits good biocompatibility with blood and soft tissues and is highly thromboresistant. In addition to being used as a bulk material for medical devices, pyrolytic carbon is also used as a coating. For example, owing to the relatively low density and brittleness of carbon, LTI and ULTI carbon coatings have been deposited on heart valve prostheses. The coatings are also doped with up to 20% WT percentage silicon to improve stiffness, hardness, and wear resistance. Calcium phosphates or cap ceramics are a material that occurs in bones and arteries in the body, and their association with the formation, progression, and arrest of enamel and dentin caries. Several different forms of calcium phosphate ceramics can be found in the human body. These include amorphous calcium phosphate, brushite or dicalcium phosphate dihydrate, monatite or dicalcium phosphate anhydrous, octocalcium phosphate whitlockite or tricalcium phosphate apatite, commonly known as hydroxyapatite. In addition to the natural forms of calcium phosphate ceramics can be synthetically produced in the laboratory. Synthetic ceramics are similar in composition, biodegradation, bioactivity, and osteoconductivity to biological apatites. The most commonly used cap phases in biomedical applications are HA, TCP, biphasic cap, and OCP. The degradation rate of cap ceramics depends on their crystallite size, degree of crystallinity, and chemical composition. Fine crystals or smaller crystallite-size cap ceramics tend to degrade more rapidly when compared to larger crystals. It is also known that the amorphous phase dissolves more rapidly when compared to more crystalline cap ceramics. In addition to the chemical and physical properties of cap ceramics, each phase's degradation is unique and depends on the phase and the biological environment conditions. Hydroxyapatite, also known as calcium hydroxide phosphate, is the most commonly known crystalline cap biomaterial. The pure HA's chemical formula is shown on the screen. Unlike pure HA, biological apatites contain chemically substituted ions found in the body. Ions such as phosphate, carbonate, and fluor can partially substitute for phosphate and hydroxide, whereas magnesium and strontium substitute for calcium. Thus, biological apatites are not pure HA. Synthetic HA can be produced using a range of techniques, including the following: hydrothermal conversion of natural coral, sol-gel synthesis, coprecipitation, solid-state reactions, microemulsion synthesis, and mechanochemical synthesis. Stoichiometric HA is known to have a calcium to phosphorus mole ratio of 1.67. Structurally, pure hydroxyapatite has a hexagonal close-packed arrangement with cell dimensions of 9.42 angstroms for the A and B lattice spacings and a cell dimension of 6.88 angstroms for the C lattice spacing. Fluorine, chlorine, and hydroxyl groups can be mutually substituted. Thus, HA, fluorapatite, and chloroapatite can conform the next empirical formula. Like other ceramics, HA is known to be very brittle but is strong in compression. Its strength is dependent on grain size, with finer grain sizes associated with higher strength. The compressive strength of HA is also dependent on its density and porosity, which in turn are dependent on the sintering temperature and time. Hydroxyapatite is classified as a resorbable bioceramic. The solubility behavior of HA is highly dependent on various factors, such as pH and the concentration of the ions present in a saturated solution where HA is immersed. The chemical reactivity of HA varies inversely to its crystalline perfection, crystal size, and crystal dimension. Large HA crystals have a lower solubility rate when compared to finer or smaller HA crystals. Aside from the physical properties, its solubility is also dependent on the biological environment, such as the solution's pH, ionic concentration, and the protonation state of the phosphate ions when immersed in a solution. Calcium ions in the HA lattice are held in place by trivalent phosphate ions. A fall in the solution pH can cause a change in the protonation state of some trivalent phosphate ions, converting them to divalent phosphate ions. This conversion weakens the calcium phosphate bonding and thus allows some calcium to be released into the solution. Divalent phosphate released into the solution binds with hydrogen ions to form monovalent phosphate ions. This binding of phosphate with hydrogen ions in the solution act as a buffer, altering the pH of the solution and slowing down the HA degradation. Hydroxyapatites can be produced as a powder, granular beads of different sizes, and scaffolds of different shapes and sizes. As it was mentioned, calcium sulfate and bioactive glasses are other examples of bioceramics. You can find some more information in the complementary material on Blackboard.